In this video, we're going to tackle the Bernoulli equation, which is actually a family of different types of differential equations that look like this. Y prime plus a function p of x times y is equal to a function q of x multiplied by, and this is the interesting spot, y to the n. You'll have noticed that we only have two major methods to solve differential equations, which is separable differential equations and linear differential equations with an integrating factor method. And this is neither of those. If y to the n was 1, then this would be a linear equation and you could use the method of integrating factors. So what I'm really going to introduce in this video, beyond just how to solve this specific class of differential equation, is how to come up with a substitution to change a new differential equation that you don't know how to do into one of the old ones that you do know how to do. Because here is the trick. I'm going to do a change of variables. I want this to be a first order linear differential equation because I know how to solve first order linear differential equations. So the substitution we're going to use is the following. I'm going to let u equal to y to the 1 minus n. So this is a definition of a new variable called u. Now, I've just sort of pulled the substitution out of thin air, but for our purposes, we're going to verify that yes, this actually works and transitions the Bernoulli equation into a linear first order, and then we'll have a little bit of practice doing linear first order equations by the method of integrating factors to get to our final answer. So what I want to be able to do, u and y are both functions of x, is I want to make some claim about what u prime is going to be. Well, indeed, this is just going to be the derivative of y to the 1 minus n, and that I can do by chain rule. So this is going to be 1 minus n is going to come out the front, and then this is multiplied by y to the 1 minus n, but 1 less than that when you take the derivative, so minus 1. And perhaps instead of writing 1 minus n minus 1, I'll just write minus n. And then multiplied by y prime. Now, what I'm going to observe here is that I have this y prime appearing in my u prime formula, but then I also can connect this to the original equation because I have a y prime there as well. So what I'm actually going to notice, and I've already circled it once, but I'll circle it a second time, I've got that y to the n in the original equation, and then I also have a y to the n, except it's on the bottom. So why don't we just align this? I'll just divide out the equation by y to the n. So that's going to give me y to the minus n times y prime plus p of x times y to the 1 minus n is equal to q of x. So that's our differential equation where I just divide it out by y to the power of n. And then I can look at the left expression, and this is pretty darn close to my expression for u prime. The only thing that's missing is this 1 minus n. So if I plug this in, this is going to give me 1 over 1 minus n times u prime. Then I'm going to have a p of x, and then y to the 1 minus n, well, that was exactly u, so I have a u here, and then just equal to q of x. All right, so I've made a change. And look what's happened. In this change of variables, the equation that I have, this one, is now a linear first order equation. It's got a u prime with the coefficient of 1 over 1 minus n. It's got a u with the coefficient of p of x, and it's got a 1 with the coefficient of q of x. This is a first order linear differential equation. Okay, so let's see how this works out in a concrete example. So I'm going to come and do, as an example, the following. Y prime minus 5 times y is equal to minus 5 halves xy cubed. That's my messy expression. And so what I observe here is that this is a Bernoulli equation with y cubed. And so what I want to do for my change of variables is u is y to the minus 2. I then continue the method, which first involved taking a derivative. So this is minus 2y to the minus 3 times y prime. I'm going to take the original equation and I'm going to now rewrite it, dividing out by y cubed in my head. So when I divide out by my y cubed in my head, I notice that first of all, I'm going to have a negative 1/2 times the u prime. That's because there was a minus 2, and I'm changing it over to the other side, so minus 1/2. And then I'm going to have what's a minus 5 times y divided by y cubed is y to the minus 2, so there's minus 5 times u. And then this is going to be equal to minus 5 halves times x, and now there's no longer a y cubed. I've divided the entire equation by y cubed. Maybe I'll put that in explicitly that I was doing a 1 over y cubed and changing to u's when I did this. And what I have now is an example of a first order linear equation as we expected. So now I'd actually encourage you to pause the video and see whether you can solve this first order linear equation yourself and see whether you get the same answer I do. And if you just want to enjoy the show, well, here's my attempt at the method of integrating factors. So when I look at this equation, The first thing I note is it is linear. U prime with the coefficient function of minus 1/2, U with the coefficient function of minus 5, and 1 with the coefficient function of this minus 5/2 times x. It's not actually yet in standard form, so that's a little trick. We've got this minus 1/2 here. So if I want to convert it to standard form, which just has a U prime out the front, then I'm going to multiply everything by minus 2. So that's going to give me plus 10x, and then that's going to be equal to 5 times x. That makes it a bit cleaner. And then I'm going to go and look at this. That is my p of x, and I use my p of x to get my integrating factor. Integrating factor is r of x is e to the power of the integral of p of x dx, which in this case is just going to be e to the power of 10x. And again, the plus c, I'll just arbitrarily set it to be 0. So then what does an integrating factor do? It multiplies all the terms. And so I have an e to the 10x times u prime, an e to the 10x times 10 times u. I see now that I had made a slight typo. I wrote plus 10x earlier. I meant plus 10 times u, so I've corrected it down below. All right, let's carry on. Is equal to e to the 10x times 5x. And the one on the right-hand side is supposed to be an x. And then we use the standard trick that we can do every time when we're doing the method of integrating factors, which is I can rewrite this left-hand side as the integral of e to the 10x, the integrating factor, and then just multiplied by u. And by product rule, that's the same thing. And on the left, nothing changes, so I'll just copy that down one more time. Okay, so that's the thing that we now want to do, but I can solve that differential equation. Just a derivative is equal to something, so integrate both sides. On the left, you get e to the 10x multiplied by u, and on the right-hand side, you have the integral of e to the 10x multiplied out by 5x. Now, we can do this integral. It looks like e to the 10x times 5x, that's going to be an integration by parts. So I'll come here and do a very quick dv and u. This u and v is just the standard nomenclature for integration by parts. I'm not trying to relate it to that u at all. This is just a temporary thing for solving our integral here. Anyways, what is it? It integrates to u times v, so e to the 10x, and then divided out by 10, multiplied by 5x, minus the integral of v to u. So I have a 1/10 e to the 10x times 5 dx. Finally, I can come here and say this is going to be e to the 10x times x divided out by 2. And then when I integrate, I get minus 1/100th multiplied by 5e to the 10x. And then I can't forget, of course, at this stage, I am going to have a plus c, and I don't want to get rid of it at this particular stage because it is important. And if we had an initial condition, then we would use that initial condition to determine the value of the c. Now we're close to being done, but still not quite. There's actually two things that remain. The first is that this expression that I have is not u. It's e to the 10x times u. So if I want to actually just get the value of u by itself, I have to divide out by 10x. So what am I going to have? I'm going to have x divided out by 2, because I'm getting rid of the e to the 10x, minus 1/20th, and then that's not multiplied by anything, and then plus c. And that gives me an answer for u, but that's still not enough. Because if I go all the way back, my original equation was written entirely, not in terms of u, in terms of y. And then I had this equation that u was equal to y to the minus 2, which if we preferred, we could rewrite as saying y is equal to u to the minus 2. So let me go back down, and this expression that I have down here for u, this is the same thing as y to the minus 2. So I'm entirely fine leaving it implicitly just like this.